Hi folks, and welcome to the third in a series of deeper dive videos exclusively for the channel's Patreon supporters, designed to take a much more detailed look at the findings contained in the AR6 synthesis report that was published on the 20th of March 2023. In this section we take a closer look at future climate change as projected by the thousands of research papers collated and submitted as part of the IPCC 6th assessment cycle. This part of the paper, at least in the summary for policymakers anyway, revolves around three infographics that have clearly been deliberately designed by the IPCC's design team to really get across the gravity of the situation, with lots of deep reds and purples on bar charts and things like that. Let's start with this one, showing how with each increment of global warming, regional changes in mean climate and extremes become more widespread and pronounced. In the language of the report, in the near term, global warming is more likely than not to reach 1.5 degrees Celsius, even under the very low GHG emission scenario, which is what we see on the left-hand side here, and likely or very likely to exceed 1.5 under high emission scenarios. In the most optimistic scenarios and modelled pathways, warming declines back to below 1.5 by the end of the 21st century. But in the very high-end emission scenario, known as SSP 8.5, the world hits 4.4 degrees Celsius by 2100. As a quick recap on IPCC abbreviations, SSPs are shared socio-economic pathways. I looked at these way back in 2018 when I was doing my little series of videos on the SR15 special report. There are 5 SSPs. SSP1 is a sustainable development pathway, which is kind of a best case scenario. SSP2 is called middle of the road development, which kind of speaks for itself. SSP3 is called regional rivalry, where potential conflicts are factored in. Does that one ring any bells, anyone? SSP4 factors in and focuses on the consequences of global inequality, and SSP5 is called the fossil fuel development pathway, which, as the name suggests, is the very worst case scenario. Overlaid on top of those pathways are RCPs, which stands for representative concentration pathways. As that name suggests, they indicate different levels of atmospheric greenhouse gas concentrations. The numbers on these things are a bit ambiguous at first glance. They don't correspond to temperature rise, as some people assume. They're actually an indication of radiative forcing as measured in watts per square metre across the entire surface of the planet. So what do I mean by that then? Well, here's a little explainer courtesy of the UK Met Office. Total radiative forcing is the difference between the incoming and outgoing radiation at the top of the atmosphere, meaningfully evaluated at the tropopause and at the top of the stratosphere. The IPCC defines radiative forcing, also known as climate forcing, as an externally imposed perturbation in the radiative energy budget of the Earth climate system, for example through changes in solar radiation, changes in the Earth albedo or reflectivity, or changes in atmospheric gases and aerosol particles. As an average across the planet, the Earth's atmosphere receives about 340 watts of incoming energy from the Sun for every square metre as measured at the top of the stratosphere. If the planet radiates 340 watts per square metre back out into space, then the average global temperature is in balance and remains unchanged. If the planet radiates more than that, then the Earth gets cooler, and if it radiates less, then it gets warmer. This chart from NOAA's annual greenhouse gas index shows how the radiative forcing of long-lived atmospheric greenhouse gases has nearly doubled since 1979, with carbon dioxide clearly shown as the main driver. The number now sits at about 3.2 watts per square metre of radiated energy being captured on average by every square metre of our stratosphere, which, as I'm sure you can imagine, is quite a big surface area. So that means less energy is escaping to space, and that's why we're warming up. RCP 2.6 indicates radiative forcing of 2.6 watts per square metre, which would represent a decrease in radiative forcing. At the other end of the IPCC projected scale of possible scenarios is RCP 8.5, representing a jump up to 8.5 watts per square metre of forcing. So SSP 8.5 is what the IPCC regard as the worst of both worlds, if you like. I'm sure you already know the statistic that for every 1 degree Celsius our atmosphere warms, it's able to retain 7% more moisture. That's just a function of physics. But to put that in the language of the IPCC report, continued global warming is projected to further intensify the global water cycle, including its variability, global monsoon precipitation, and very wet and very dry weather and climate events and seasons with high confidence. So if we look at this middle set of maps, we can see how the moisture in our soils will change with increased warming. It's measured against the standard deviation of interannual variability in soil moisture between 1850 and 1900, which apparently is the widely used metric in characterising drought severity. A projected reduction in mean soil moisture by 1 standard deviation corresponds to moisture conditions typical of droughts that occurred once every 6 years during the latter half of the 19th century. Even though there's more moisture in the atmosphere overall, the distribution of that moisture will be highly variable. So while the Amazon dries up and becomes a savanna, and the western side of America, most of southern Europe and large parts of China experience severe droughts that make today's situation look like a walk in a park, Africa and the Middle East and the middle part of Asia all get wetter. Now you might think a bit of extra water would be no bad thing in those areas, but the trouble is it comes as huge deluges in monsoons and other extreme events, as we can see if we go down to the bottom set of maps. These show a 40% increase in annual wettest day precipitation over the top of Africa, across into Asia and right across the Pacific Ocean, as well as at the poles. And to give you that in the more correct language of the IPCC, the report states with high confidence that with further warming, every region is projected to increasingly experience concurrent and multiple changes in climatic impact drivers. Compound heat waves and droughts are projected to become more frequent, including concurrent events across multiple locations. Due to relative sea level rise, current 1 in 100 year extreme sea level events are projected to occur at least annually in more than half of all tide gauge locations by 2100 under all considered scenarios. Other projected regional changes include intensification of tropical cyclones and or extratropical storms and increases in aridity and fire weather. That takes us to the next colourful chart full of cheer and optimism. This one deals with the severity of impacts across natural and human systems. Here's where we start to get an overview of the damage we're causing to all the other species on the planet. These maps show the percentage of animal species and seagrasses exposed to potentially dangerous temperature conditions, and at the higher end of the scale, it's clear that towards the end of the century, pretty much 100% of all animal and seagrass species across the mid-latitudes fall into that catastrophic category. Then we've got days per year of human population exposure to conditions that pose a risk of mortality from surface air temperature and humidity conditions. You may remember I did a video about wet bulb temperature last year, and you can click up there to jump back to that. Essentially, at a temperature of just 35 degrees Celsius with 100% humidity, the human body is not able to sweat to evaporate enough heat away from the body in order to stay alive. So anyone outside in those conditions for more than a few hours, even if they sit still and in the shade, will be at the risk of dying. Countries in the mid-latitudes are kind of used to this already. Manual workers outside often simply have to down tools and take cover in the hottest parts of the day to avoid ending up in hospital that evening. But North America and Europe are far less well prepared for such conditions. So we've got a big shock coming our way, according to these charts. Then there's the bottom three maps that consider impacts on food production. As one of our most important cereal crops, maize is a good indicator of land-based food production impacts. Yield levels during the last 2 decades of this century are projected to be as much as 35% lower across the Midwest of America and between 15 and 30% lower across southern Europe, sub-Saharan Africa and large swathes of Asia, including China. Southern Africa and some parts of northeastern Europe may see crop yields increase, but I think it's fair to say that it doesn't look like being enough to compensate for the losses. And the final set of charts represent what the IPCC very politely refers to as reasons for concern. I imagine you've seen these bar charts before. I've certainly referenced them a few times in previous videos. The summary chart at the top of the page considers 5 main categories: unique and threatened systems, extreme weather events, distribution of impacts, global aggregate impacts, and large-scale singular events. Essentially, the darker the colour, the worse the risk. What we've got in this top section are 2 bars for each category. The narrower bars on the left of each category show the level of risk projected back in 2015 in the IPCC's 5th assessment. Since then, the report says that the continued increase in greenhouse gas emissions, combined with much greater levels of understanding of the impacts, means those bars have had to be upgraded to the ones shown on the right of each category. So now we're looking at high or very high risks at temperatures above 3 degrees Celsius in every single one of the 5 categories. If we drill down a bit further, we've got potentially as many as 100 million additional people exposed to wildfire risks and very high permafrost degradation, biodiversity loss, and water scarcity in land-based systems, plus the well-publicised die-off of the coral reefs and high risk to kelp forests and seagrass meadows in marine ecosystems. This particular section of the report concludes that some future changes are now unavoidable and possibly irreversible, but they can still be limited by deep, rapid and sustained global greenhouse gas emissions reductions. In the next video, we'll take a look at carbon budgets and how the IPCC says we might be able to stay within them. So thanks for sticking with me this far, and hopefully I'll see you in the next one. Bye for now.